tell you a little bit about our research, which is really research of my students, Yu-Cheng Lo, Joey Gonzalez, Apo Kirola, and Jay Gu, and my postdoc, Danny Bixson. And my basic area of research is machine learning. And what we really like to do is address machine learning in the context of big data. And we built a system called GraphLab, which is gaining a lot of popularity in the industry. And so I'll tell you a little bit about that system. But more importantly, let's start thinking about the challenges of big data. So it's pretty clear today that the sizes and complexities of data sets we'd like to deal with have increased tremendously. And this idea of data getting bigger was well exemplified in this article from the New York Times maybe a couple of months ago, where they basically said that big data has become an economic asset like maybe currency or gold. And that might be true, but it's only true if we're able to extract value from data. Just storing data is not enough. And I believe strongly that extracting value from data requires us to do very deep data analysis, and this is where machine learning comes in. But the challenge is that people like me who have worked in machine learning for years have really not understood how to do it in the context of these new computer architectures like the cloud and really parallel computing systems. And what happens is that machine learning experts, or if I'm true to my group, really my graduate students, end up solving the same problems again and again and again, dealing with things like race conditions, distributing state, race conditions, communication, race conditions, and these are really things that I don't understand. I really don't know what they are about. And the code that comes out of my group, or was coming out of our group, ended up being impossible to maintain, difficult to understand, nobody could debug it, and nobody could use it in the long run. So we ended up with a bunch of useless code. And because of that challenge, many people in my field have moved to higher level abstractions, higher level ways of programming the cloud. And perhaps the most popular way these days is the so-called MapReduce abstraction, which is exemplified by Hadoop. And here's a very simple example to understand it. If I have a ton of images, let's say on Flickr, and I'd like to extract images, I'd like to extract faces in each image independently of each other, MapReduce is the right solution for you. It sends images to different processors or different machines, extracts faces, and makes some kind of local classification. And so this is good when you have a ton of highly independent subproblems. And if we look back and we step back and thought about machine learning, which parts of machine learning were really a lot of highly independent subproblems, we came up with things like feature extraction, extracting faces and features, or computing high-level statistics like the counts of different words in a big data set. But the question that challenged us is, what is there to machine learning that does not fit into this Hadoop kind of model? I think that getting value out of big data, it's about making connections. It's about connecting things together that are not independent. So this is the power of dependencies. Let's say that I take this image and I label the face of the image, my grandma. And I'd like to propagate this information throughout my database of images. So here's another image, and here's a face that was detected. The problem is that there is not a strong enough similarity between these two faces to say that this other image is also my grandmother. And what else could we do? What we can do, and here's where the power of dependencies come in, is to be able to take images from my database and find similar faces on multiple images and start connecting them together in graphs. And if I do these connections and I build this set of similarities, I can discover, for example, the fact that two people co-occur in one image and then they co-occur in other images. This tells me some information about who that person is. So my grandma co-occurs with my aunt in two images. So this other image might be an image of my grandmother. So if I propagate information through this graph of dependencies, I can make better predictions. So this is an example with making predictions of who's in an image. Here's another example where propagating information from a graph is quite important, and we're all familiar with this example. Let's say that I want to make movie recommendations. Now, sometimes you have an easy case. For example, let's take that this user, let's say that this user liked Lord of the Rings, but for some reason did not like Star Wars 4, but liked Star Wars 1. Not sure who this user is, but the geeks will understand why I suffer. And also liked Harry Potter. So for this type of user, maybe it's pretty easy. Maybe I can say, okay, Pirates of the Caribbean might be a good recommendation. But let's take another user. Let's say that I like Women on the Verge of a Nervous Breakdown, The Celebration, City of God, and Wild Strawberries. What would you recommend I watch? This might be slightly more complicated. What's that? Episode 4, exactly. Very good. The example Gaetan is for you, by the way, what I recommend. So the way that we've been doing this with collaborative filtering in the industry is to say, well, there are other users in this network, and users who like similar movies to me, and maybe this new user also liked La Dolce Vita, and so perhaps a good recommendation for me is La Dolce Vita. And so propagating information around this graph lets me make better predictions. Here's the final example that I'm going to give. Let's say that I want to analyze documents and discover topics so I can recommend books that you're interested in reading. What you can do is take books from a database of books and the words and associate them together in graphs and use what's called a topic modeling algorithm to discover that there are certain topics embedded in these books that are of interest. So topics like Apple, computers, or most importantly, cats. And then for different users, you can figure out what topics they're interested in and be able to recommend books of similar topics. And if you run this on Wikipedia, for example, you'll discover topics around art, cars, radio, television, and so on. So these topics are discovered from data, and they're fundamental for recommending products. So if I step back and look at the machine learning pipeline, you can say that you start from data. That might be images, documents, movies, and so on. You extract some features, for example, faces in the image or words in the document, and you connect them together in a graph, and you do what's called structured machine learning, structured analysis on this graph, and that's what gives you value from the data, in my opinion. This beginning of the pipeline, this part in blue on the left, is what I call the graph ingress problem, and it's mostly well done with data parallel methods with Hadoop. So for those of you familiar with Hadoop, the part on the left is well suited for it, and it's what we've been doing in the industry quite well so far. The purple box is where the challenge begins, what we call graph structure computations. So if I think about and go back to the question, what is there to machine learning? So the types of data analysis you can do with Hadoop are quite different than those you can do well with graph structure computation. And those on the right are just some examples of algorithms, but are the fundamental things that you want to do with social network analysis, collaborative filtering, product recommendation, graph analysis, and so on. So let me give you an example of a graph parallel problem. Let's say that there is a social network, and I would like to figure out who to advertise to. And here's a particular user. I might say, what is the rank of this user in the social network? It's hard to understand in isolation, but you can say, okay, it depends on the rank of the users who follow her. That's good. And what is the rank of the users who follow her? Well, depends on the rank of the users who follow them. And this idea of the rank of the users who follow you and iterating through this loopy graph is what the Pagerank algorithm, for example, that Google used over a decade ago, is quite good at doing. They did it for web pages, but it's quite popular to do it today in terms of social networks. The idea is very simple. What is my rank? It's the weighted average of my neighbor's ranks. And you keep iterating, my rank is the weighted average of my neighbor's rank, until you converge to some solution that gives a rank to every user in the social network. So this gives you an idea of what is a graph parallel problem. You start with a graph. You define an update, like my rank is the weighted average of my neighbor's ranks. And you iterate with these updates again and again and again until convergence. We call this graph parallel algorithms, and they require graph parallel abstractions, not MapReduce, not Hadoop, but something new. And this was the inspiration of the start of the Graph Lab project a few years ago. We were very focused on the needs of machine learning, and our dream for this project is that a machine learning expert or a graph analysis expert would come in and say, I know how to solve a problem on this graph on one machine. Now give me Amazon EC2, the cloud, or even a multi-core machine, and I'm going to efficiently give you parallel predictions without having to worry about any of those race conditions and communication issues and so on. That was our goal. And that led to Graph Lab 1, which we released maybe a little bit over a year ago. And I'll just give you 2 slides, a sense of what it's about. It's a way of representing data, so it allows you to represent graphs. In the social network example, vertices might have data like a user's profile, on Facebook, and edges might have data like, here's the similarity between this user and neighboring users. And then we perform computations on this graph. And the question is, how do you define computations on the graph? The way to specify computations is to think like a vertex. So how does a vertex think? A vertex thinks by looking at itself and the neighbors on the graph. So you start with a vertex, and you're able to look and modify data in the neighborhood around it. So for example, for the PageRank algorithm, you get to read the rank of neighboring vertices. Again, you don't have to pay attention to the formulas, but you get to read the rank of neighboring vertices. You get to update your rank as the weighted average of the neighbors' ranks. And then you get to tell your neighbors that your rank has changed sufficiently that they have to go around and schedule their computation, revisit their beliefs about the world. And GraphLab allows you to think like a vertex in many different ways with user-tunable models, which I won't get into, but I believe are pretty interesting. But let me give you a sense of one of the questions that happens, of one of the issues of parallelism. Let's say that there is these 3 red vertices processing their data at the same time. And so they can modify data in neighboring vertices. Let's say that the blue vertex starts to operate at the same time. Since the scopes of these vertices overlap, you might have a race condition. You might have 2 people trying to write to the same data at the same time. And this can lead to inconsistent solutions. When I started this project, a bunch of people came to me and said, oh, machine learning algorithms, these are all statistical. Forget these inconsistent solutions. You don't have to worry about them. Just go ahead and ignore them and hope for the best. What they were telling me is that no consistency lets you have higher throughput. You can do more updates per second. And for those of you with big families, you know that you're talking at a table, you just talk on top of each other. You can talk more often, but nobody knows what anybody else is saying. And machine learning algorithms feel the same way. Even though you can do more updates per second, often you can have slower conversions or even diversions. Let me give you an example of that. So what I'm showing here is a graph for Netflix data. On the x-axis is the updates as the algorithm progresses. On the y-axis is the training error. So we want to get to the bottom of this curve. If you allow people to talk on top of each other or have inconsistent solutions, with only 8 cores, so that's not many people on the table, this is the kind of answer that you get. It doesn't converge, it oscillates a lot, gives you inconsistent values. But if you guarantee consistency in your model, this is the kind of solution that you get. We quickly converge to the correct answer. So GraphLab guarantees that for you without having to worry about anything. Guarantees consistency and allows you to tune the level of consistency that you want. GraphLab is about graphs, is about update functions, and is about guaranteeing consistent computations. A lot of people are implementing algorithms on top of GraphLab. It got picked up by many groups in the industry. A lot of companies were using it, some large companies, many startups. And just to give you a sense of performance, Tom Mitchell's group at Carnegie Mellon wanted to solve a problem that was in natural language processing using the co-EM algorithm. The problem was perhaps too large to solve, and they were having trouble with one machine, so they decided to go use Hadoop. And they felt good, because they could run on a Hadoop cluster with about 100 processors and solve this problem in 7 hours. They couldn't solve it before, they used Hadoop, they could solve it in 7 hours. But then they learned about GraphLab and implemented a version of GraphLab, and with 16 cores, they could solve the problem in 30 minutes. So that's 6 times fewer CPUs, 15 times faster. Now, of course, Hadoop is a cloud-based system. 16 cores was a single machine. What happens if you use a cloud version of GraphLab? Well, with 32 EC2 machines, you can solve the same problem in 80 seconds. That's 0.3% of Hadoop time. And if you're paying for computing time, 2 orders of magnitude faster is 2 orders of magnitude cheaper, so that's always a good thing. So as I mentioned, this was a result from about a year ago, and GraphLab was getting a lot of traction, and we were feeling very good about ourselves, and perhaps we got a little ambitious. So I sat around with my students and said, oh, what is the largest graph that we have available from real data? And there was this, Yahoo put out this Alta Vista version of the web graph from 2002, which had about 7 billion edges in it. And we said, okay, let's run an algorithm on top of that. Nobody had any published running time results on this graph with 7 billion edges. Let's run GraphLab. And GraphLab failed miserably. It did not work. We could not solve a problem in this graph. And we just did not understand why. And after stepping back for a bit, we realized that this graph had a very interesting property. It's what's called a natural graph. So I don't know how many of you have seen natural graphs, and I'll give you a little idea of it right now, but these are graphs that come from natural phenomena. And GraphLab and other abstractions out there were not good for them. And the problem is that many of these abstractions assume more or less simple graphs, things like grids, where you have low degree distribution, so every vertex doesn't have that many neighbors, and they're easy to partition across machines. While natural graphs and real-world graphs don't have that property. They have what's called power law degree distributions, and they're very hard to partition across machines. And just to give you an example of what that means, if you take the web graph from 2002, about 100 million vertices only had one neighbor. These are like a few, of our friends or myself who doesn't have that many friends, These are the sad ones on the left. On the other hand, they're the popular ones, like 1% of the vertices on the web touch 50% of the edges. And that's a tremendous, tremendous set of high-degree vertices. And this is not just true on the web graph. In a social network, you have very popular people who are connected to many others in the social network. On a movie recommendation system, you can have a movie that everybody watches and rates. In machine learning models, you have something called hyperparameters, which are connected to every variable in the process. And in text analysis problems, you have very popular words that appear in many, many documents. And when you have these very high degree vertices, things can get really bad. So just to give you a sense of what happens, for example, you have a very high degree vertex and you try to partition across machines. You end up having many edges that cross the boundary of machines, and the amount of data that needs to be transmitted is linear on the number of edges that cross boundaries, which in this case is very large. And it turns out that there's a theorem, very beautiful theorem, that says for natural graphs, even if you could solve this NP-hard partitioning problem, you still wouldn't get a low-cost partition. So these are problems that are pretty impossible to solve. And because they're impossible to solve, everybody uses what's called hash partitions or random partitions. It's the obvious idea. You just assign vertices to random machines. And proof by PowerPoint, you cut a lot of edges. And in fact, it's easy to prove that if you have 10 machines, you're going to cut 90% of the edges. And if you have 100 machines, you're going to cut 99% of the edges. And so you're transmitting a lot of data back and forth. And based on these observations and the fact that GraphLab and other systems were failing, we realized that you can do something different. And this is where GraphLab 2, when the latest version of GraphLab came out. And rather than partitioning edges across machines, what we're doing is taking these high-degree vertices and cutting them across machines. So it's a new type of graph cutting process, and I won't go into details, but you'll still be thinking like a vertex. You'll still be programming like you do in the left side, but it gets executed like it was on the right side. So this is the question that we try to solve, and how does the abstraction do? It works by noticing that for many problems like PageRank that I described earlier, processing goes into three phases. First, if you're a vertex, you gather information about your neighbors. Then you change your mind about what you believe about the word. Then you tell your neighbors something. And we call this the gather, apply, scatter model. You gather information about your vertices, about your neighbors. You apply something to yourself, and then you distribute it to your neighbors. Let me give you another example of this. Social networks. Lots of companies are interested in finding influencers in social networks. And for a while, they were trying to find influencers by saying, oh, pick somebody who has many friends. So somebody who's an influencer is somebody who has a high degree in this graph. But what people have found is that this is not a good metric. A better metric, or one better metric, is to say an influencer is somebody who's part of many triangles. That is, I have many friends who are friends between themselves. And this is a measure not just of popularity, but of cohesiveness. Because if I advertise to somebody who's part of many triangles, they'll tell their friends, and the friends will tell each other, and the stories just propagate more densely, and you get more value out of your money. Again, this is another example of a graph problem, detecting these people with very high number of triangles, and you can put them in this new GraphLab 2 abstraction too. You can gather information about your neighbors, which is just gathering the list of neighbors that you have in a very natural way. I learn my list of neighbors, and in the scatter process, or in the second phase, I compare with my neighbors, and I say, oh, you're neighbors with that person, I'm also neighbors with that person, we're a triangle. It's kind of like the game set. You see those sets, and you say, oh, here's a triangle. So let me give you an example of what happens when you run that. If you look at Twitter in 2010, this is the data that we have, highly popular people were people like Britney Spears, which had many, many neighbors. But people in strong communities with many triangles are people like Stephen Colbert. And if you believe in this model, it's better to advertise to Stephen Colbert than it is to Britney Spears. And if you know, for example, what Stephen Colbert did to Wikipedia many times, like changing information that's true, maybe you'll understand why, because his community is so close. So GraphLab 2 addresses this and addresses this new type of data partitioning problem when we take big high-degree vertices and split across machines. Communications that you have to do is linear in terms of numbers of machines where vertex gets split to. This is called the vertex partitioning problem. There's a nice theorem that says that it's possible to do this even in natural graphs. And in GraphLab, there's some very nice algorithms that guarantee it. So I've talked about abstractions. I talked a little bit about examples of machine learning. I talked about the GraphLab process that we've been building, but we also have a system available that lots and lots of people have been using it. The system is built on top of standard cloud infrastructure that I'm sure your company is already familiar with, so things like Hadoop and so on. We have our own infrastructure built on top of it that does what GraphLab needs to do. You don't have to worry about that. There's an abstraction on top of it, and you can write machine learning algorithms or data analysis and algorithms on top of them. But we've also provided a number of different toolkits on things like graph analysis, collaborative filtering, computer vision, clustering, topic modeling, and so on. And a lot of companies today are using these toolkits directly rather than writing their own algorithms. So there's a trade-off between the two. So this is the GraphLab system. GraphLab 2 system. Let me show you a couple of results. So I mentioned triangle counting in Twitter 2010. The graph had about 34 billion triangles to be counted. That's a lot of triangles. And in 2011, so that's last year, the best published result for solving this problem used Hadoop. They used about 1,500 machines and took them 400 minutes. Using GraphLab 2.1, we can solve this problem in 1.5 minutes with 64 machines. And you can ask why. Why is this the case? I won't show you the math, but the reason that it's the case is that Hadoop is just the wrong abstraction for graph parallel processing. It does a lot of communication that's unnecessary because it doesn't understand the structure of the graph. And this is where the gains of GraphLab come in. So you can say one way of declaring success is speed. Speed is good. You want to be faster. But that perhaps is not the only measure of productivity that you have when you're trying to do large-scale data analysis. So here's another measure of productivity you might have. Let's say that you're analyzing text data from Wikipedia. This is all of Wikipedia. People want to do that kind of text analysis that I mentioned in the beginning of the talk. Yahoo wanted to do this. It's very core to their business. And they built a system just for this problem. It's a very beautiful system. And on 100 machines, they can process 150 million tokens per second, which is very impressive. And it took them a long time to build the system. We ran this problem on GraphLab, and on 64 machines, we could process about 110 million tokens per second. The difference is the Hadoop system took a long time to engineer and build. The GraphLab system, my student spent 4 hours and wrote 200 lines of code. So maybe productivity is speed. Maybe productivity is engineer time. But I think both of these things are very fundamentally important here. Third notion of productivity is money. So if you're looking at doing PageRank, for example, on the Twitter graph, if you're using Hadoop, it takes about 5.5 hours. If you use an in-memory version of Hadoop, it takes about 1 hour. With GraphLab, it takes about 8 minutes. So if you're paying for computation, this one costs $180, this costs $41, and this one costs $12. So this is GraphLab 2.1. And then my student, Apokirala, walks into my office. He says, I believe I can solve very large problems on a Mac Mini. The way he did that is to exploit SSDs and hard drives. And the challenge here is that if you're trying to use hard drives or SSD, if you have random access to the data, for example, data on one part of the graph comes from one part of the disk, while the other one comes from a different part of the disk, it's going to be extremely slow and unusable. And he came up with a novel type of data structure that minimizes the number of random accesses in the disk. It's very cool. And the only thing that I can tell you right now of how cool it is by example. So let's say counting 34 billion triangles. On Hadoop, it took about 400 minutes. On GraphLab 2, it took 1.5 minutes. GraphG uses the same abstraction, so the same code from GraphLab went into GraphG, and he can solve this problem in 59 minutes on a Mac Mini. It's pretty cool. And not only that, he can deal with streaming data. So rather than graph being static, you can imagine Twitter is continuously generating tweets and parts of this graph, and he can read in about 100,000 edges per second at the same time as he processes 200,000 edges per second on a Mac Mini. So these are two examples of systems that we've built for very large-scale machine learning on the cloud with a different type of abstraction they would be doing with Hadoop. The two systems are GraphLab for the cloud and GraphG for a single machine. And they're both available on Apache license and both being picked up by a bunch of different companies, but I would be very happy to interact with anybody here who's interested in these ideas. Thank you.